Hi everybody, this is the lecture on section 5.4, which is on some comparison tests. So the first comparison test is as follows. So the basic comparison test uses inequalities. If AN is bigger than or equal to sequence BN, is bigger than or equal to 0, then 1. If the series AN converges, then the series BN converges. Essentially, the sum of the A's is greater than the sum of the B's. So if the sum of the A's is finite, so is the sum of the B's. Right? The partial sums, because it's a positive, non-negative series, because it's a non-negative series, the partial sums form an increasing sequence. And that increasing sequence is bounded by the limit of AN, the sum of AN. So essentially, if this one is finite, so is that one. 2, the other way around, if this one is infinite, the smaller one, then the bigger one must be infinite as well. If the sum of Bn diverges, it must be because it's infinite, because it's a positive term series. Then the sum AN diverges. Okay? So, for example, the sum 1 over 2 to the n plus 1 converges, n equals 0 to infinity, converges or diverges. Okay, not what does it converge to, but just does it converge or diverge. Okay, well, because 2 to the n plus 1 is greater than 2 to the n, 1 over 2 to the n plus 1 is less than, 1 over 2 to the n, and certainly it's bigger than 0. Positive numbers for n is bigger than or equal to 0. Therefore, because the sum 1 over 2 to the n, which is the sum n equals 0 to infinity, 1/2 to the n, converges, why? It's a geometric series. With ratio 1/2, which is less than 1. So because this series converges and this one is smaller than that, we must have that sum n equals 0 to infinity, 1 over 2 to the n plus 1 converges as well. Okay. Another example something like this. The sum n equals 1 to infinity, 1 over the natural log of n. So this one I'm not sure if we did this already in section 8.3. I believe we did one like it. Yeah, we did one like it. Anyway, so this one here, I guess we got to start at n equal to 2. So here, 0 is less than or equal to 1 over natural log n. Right? Natural log is a positive number for n's bigger than 1. But that's less than 1 over n. Right? The natural log of n, that's your typical slow-growing function. So it's a function that looks like this, right? Like, here's the point 0, 1, and then well over here, here's e, right, which is 2.7 something, and at e, we're all the way at 1, right, but yet the line y equals x is over here. Right, so x is bigger than the natural log of x, therefore the fraction 1 over x is bigger than, I'm sorry, the other way around. X is larger than for n's bigger than or equal to 2. So 0 is less than or equal to 1 over n, well, strictly less than, is less than 1 over natural log n. Right, because the denominator, the natural log, is smaller than the denominator of 1 over n, the fraction is bigger. So, because the sum, n equals 2 to infinity, 1 over n diverges, we must have that the sum n equals 2 to infinity 1 over natural log n diverges as well. Okay, so that's the basic comparison test, and it's somewhat limited in scope in that you always have to have these strict inequalities. Bigger than or equal to, less than or equal to, but it may not be the right inequality, like, you know, for what you're trying to prove. So there's something a little bit more general than this basic comparison test, and it's called the limit comparison test. Says the following: if an and bn are sequences of positive terms, and the limit as n goes to infinity of an over bn is equal to L, and L is not 0, and L is not infinity, then the sum of an and the sum of the bn both converge or both diverge. Okay, so that's the first item in the limit comparison test. If the limit of the two sequences over each other, this ratio is L, and L is not 0 and is not infinity. So you've got a limit, and the limit is neither 0 nor infinity, then both series for an and bn, they both converge or both diverge. 2. If the limit as n goes to infinity, an over bn is equal to 0, and the sum of bn So this going to 0 says Bn is large. Then if the sum, wait 1 second. If this limit an over bn is 0, in other words, bn is large compared to an, and bn converges, then an converges as well. Three, if the limit as n goes to infinity of an over bn is infinite, in other words, an is large compared to bn, and the smaller series bn diverges, then some an diverges as well. Okay, so 3 types of ratios here. A ratio that converges to something other than 0 and infinity, ratio that converges to 0, and a ratio that converges to infinity. When you have the limit is not 0 and not infinity, then both series converge or diverge. When you have that the limit of a over b is 0, that means b is a lot bigger than a, by comparison, as n goes to infinity. So if this bigger guy, the sum of the bigger series, is finite, then so is the sum of the smaller series. And the other way around, if an over bn is infinity, meaning an is larger than bn, and the smaller one, bn, diverges, then the larger one has to diverge as well. Okay? So a couple examples for this one. So suppose we have the sum n equals 1 to infinity, n over the square root n to the 4th plus 1. So notice that converge or diverge. We sort of have polynomials on the top and bottom. Okay, so let's compare to something that has polynomials on the top and the bottom. What's the highest power of n on top? Well, it's n. What's the highest power of n on the bottom? It's n to the 4th. Well, but this square root on the outside here kind of makes it like an n squared. All right, so let's compare this to 1 over n. All right, highest power of n on the top is n, highest power of n on the bottom is n squared. That's equal to 1 over n. Okay, let's look at the limit as n goes to infinity of this series. 2n to the 4th plus 1 over 1 over n, like this. This is the limit as n goes to infinity. N squared over square root 2n to the 4th plus 1. So this is the limit as n goes to infinity. Divide the top and bottom by n squared. So we have the limit as n goes to infinity. On the top here I have 1, and then on the bottom the n squared comes inside the square root and becomes the n to the 4th. Alright, so this is equal to the limit as n goes to infinity, 1 over, well, this is 2n to the fourth over n to the fourth as n goes to infinity. Polynomials of the same degree, fourth power, fourth power. So the limit as n goes to infinity is just the ratio of the leading coefficients. So this limit is 1 over root 2, which is not 0, and it's not infinity. Thus, this series, the original series, n over, and the series we compared it to, both converge or both diverge. Well, we know this one diverges, so they both must diverge. Right? That's the harmonic series. That's the basic example, of a series that diverges even though the terms go to 0. And we talked about this one on the section on the integral test, the last section here. So these two both converge or both diverge, but this one diverges, so this one diverges as well. So when you have a series with polynomial expressions, a rational function essentially, ratio of polynomial expressions, you compare to a p-series, where you take the highest power of n on top and the highest power of n on the bottom and cancel out and see what you have left. And that's what you compare it to when you have these so-called rational expressions. How about this one? All right, converge or diverge. Well, and notice you've got this 2 to the n on the bottom, this exponential function. Exponential functions, they're very fast-growing functions, and essentially they beat out polynomial functions. So, I want to compare this to not a rational function, but this exponential function. So let's compare to 1 over 2 to the n, which is 1/2 to the n. Right, and we know that, that series of 1 over 2 to the n, it converges because it's a geometric series whose ratio is less than 1. Well, anyway, let's look at the limit. N squared plus 1 over 2 to the n times n squared over 1 over 2 to the n. So this is the limit as n goes to infinity, and the 2 to the n's cancel. And I'm left with n squared plus 1 over n squared. And as n goes to infinity, these are both degree 2, so the limit is the ratio of the leading coefficients, which is 1, which is not 0 and is not infinity. Therefore, this series here and both do what? They both converge or both diverge. But this one is a geometric series whose ratio is 1/2, which is less than 1. So that one converges, so they both must converge. Not that we know what this is converging to, but it does converge. Okay? So there's just those two topics in this section, just the two comparison tests. And so that will conclude the lecture for this section.